Hi, my name is Shayla Rich, and this is Lab 5, the Falling Slinky. Alright, so the purpose of this lab experiment is to use experimental and computational models to predict the motion of a slinky when dropped from a certain height. Some of the relevant physics principles are Newton's second law, which we'll be using to help determine the forces that keep the slinky balanced, the position update formula, and the velocity update formula, which we're going to be using in the code to track the position, and also the gravitational force. I couldn't find a picture, but the drag force is also relevant here because the slinky is being dropped through the air. Alright, for a brief overview of the results, the bottom of the slinky actually will not move until it makes contact with the top of the slinky. There were some slight inaccuracies due to errors in the experiment or maybe the drag force, but overall this is what the experimental model looked like. Alright, so for the procedures, first we're going to put the video of the falling slinky in Tracker, then we're going to obtain points at each time interval. Then we're going to create a computational model in GlowScript based off of the video of Tracker, and then we're going to discuss the results. Alright, for the experimental model, the system in this case is the slinky, and the surroundings are everything else that is interacting with the system, so the earth, the wind, things like that. Alright, so for the initial position, we just took it from the Tracker video. So we have the time, the x position, and the y position, and the initial velocity is just 0, 0, 0 because the slinky started from rest. Alright, for the computational model, right here under the initial conditions, I have the mass of the spring, which I just used based on a Google search to determine what the average slinky weight would be. We have the initial position and the initial velocity, which we got from Tracker, the gravitational constant, proportionality constant for the drag force, which we're going to be implementing in the computational loop. We had to figure this out through just some experimentation after we got the code written. Here are the time steps. This is where we determine the force of gravity before the bottom of the slinky starts moving. So force of gravity, the upward force of the tension, which keeps the slinky from immediately falling down, and then the net force at that time. And then after the bottom of the slinky starts falling, we calculate the drag force and then the net force. Here is where we do our position and velocity update formula, and right here is where we plot it. Alright, so for the computational results versus the experimental results, you can see that numerically they're very, very similar, but there were a couple of discrepancies over in the experimental because of probably where I place the center of mass during Tracker. Alright, so for possible sources of error, human error, input errors, I could have inputted something wrong in the code. Any unknown forces acting in the experimental model could have given us slightly different results, and there also could have been inaccurate drag force. For the discussion, why do we only include the drag force after the top of the slinky hits the bottom? So even though the top of the slinky is moving, the bottom of the slinky does not move until after it gets hit. In that case, the actual position of the slinky begins to change, after the bottom of the slinky starts to move. Drag force only works on moving objects, and the slinky is only considered moving once the bottom starts to move. What if the slinky was dropped on the moon instead? If the slinky was dropped on the moon, the same physical behavior, i.e. the bottom not moving till the hops hit it, would be shown. However, because gravity is 1/6 of the gravity on Earth, the top of the string would fall more slowly, and there would also be no drag force because there isn't an atmosphere on the moon. So the bottom of the slinky would fall to the ground at exactly the rate of gravitational acceleration for that of the moon. And the final conclusions: before the top of the slinky hits the bottom, the upward tension and downward gravitational forces at the bottom of the spring were equal. So that's why it wasn't moving, because the tension that was going upwards before it was hit from the top, and there was also an equal force going down. It was a good representation of Newton's second law and balanced forces. Thank you for watching.